Yeah. So I had, I think the last lecture I had gone up until this particular slide. So just as a recap, what we had talked about was, some details of machine learning. Yeah.
Just 1 moment. Yeah.
Oh, okay. Sorry. Yeah. Sorry, I thought that I could start. Yeah. Just let me know when it's okay. Hello.
Just a minute.
Oh, yeah, sure.
This meeting is being recorded.
Okay, now you can share. Yeah.
Yeah. So is my screen visible? Because I think the share is still active on my end.
Let me see.
Okay, I'll just stop and start again. Yeah.
Yes, Digant, I can see it.
Okay.
Not now, I cannot, of course.
I'll just start again.
Yeah. No, you're fine. You're visible. Easy.
Yes, I can see it.
Not here though.
But I'm a minority here. So.
No, I can hear everyone.
Yeah, but your screen is still not visible here.
Okay. I think I stopped and started again. It might be that it'll just take a few moments to appear. Is it still not visible?
No.
Oh, I see.
Maybe you could get out and log in. I mean, get in.
Yeah. Should I leave and leave and log back in? Yeah.
No, there. இங்க விசிபிளாகவே இல்லை அது இது போயிட்டா இது தெரியுது இல்லை மறுபடியும்
Hello, can you hear me?
Okay.
Can you?
Yeah, I have made you co-host.
Yeah.
Hopefully this time you should. Now it's visible.
Okay. Okay.
So how do I make it full screen?
Minimize this.
Yeah, you're way wrong.
Okay. Okay. Sure. So just as a quick recap, what we had seen in last class was some more details about this gradient descent and training neural networks by gradient descent. So neural networks are these parameters function approximators. And then we can think of training as finding these parameters theta, which are these weights and biases, by optimization, right? So then there are two like high-level questions. What are these, what is the loss function on theta that we should optimize, right? Like theta is just some weights and biases. How do we choose what function of theta to optimize, which is, how do we choose the loss function to optimize? And then how to optimize, right? So we looked at the first question in details, choosing the loss function. So we said that, okay, it can be sort of looked at as for this classification problem. We looked at this digit classification problem, right? So there we saw that, okay, choosing a loss function basically boils down to choosing a way to interpret the output of the neural network as a distribution, and then looking at distances between the distributions given by the output of the network and the actual distribution predicted from the data, right? So this can be done, as we said, interpreting the output of the neural network as a distribution can be done via the softmax. And then the cross entropy will be able to measure differences between the distribution given in the data and the actual distribution. The actual distribution in the data and the distribution produced by the neural network. And the average of the cross entropy is basically how one can define this loss function, right? And so this was regarding how, what do you optimize? And then we've gone into, went into this gradient descent procedure where we are talking about how do we actually optimize things, right? There we gave this general approach of gradient descent where we calculate the gradient of the loss function. And then we just update this weights and biases theta in a direction opposite the gradient, right? So this is basically we're descending along the gradient. So it's called gradient descent. And we talked about how this will be repeated until some optimum is reached, and we discussed how you can detect or decide when you've reached an optimum and so on. And we also talked about some general shortcomings of this, right? In that there are no guarantees, and whether it will converge or not. And even if it does converge, unless it is convex, we don't know whether it has converged to the global minimum or not. In general, we can only say that, okay, if it has converged, then whatever it has converged to is a local minimum. We cannot really say anything more than that, right? So this is what I had at the last time, and now I just have a few more slides going into a little bit more details about how do you calculate the gradient, and some discussion about some of the issues one might face in general during training. So before I go into that, I want to ask if there are any questions on the previous, like on these slides.
Any questions? No, there's none here. You can go ahead.
Okay, so yeah, so then there's two things that are still left in this algorithm, right? So we have said that, okay, we're going to calculate the gradient, but how? So if you remember, this L is a fairly complicated function, right? It is definitely differentiable. That much we have checked. But if you go back to the definition of L, it is this average of this cross entropy, and this cross entropy is again this sum of some something into log of something, and then this pk itself is again this ratio of exponentials and so on. And of course, then each value that is going into the exponential is again coming from a neural network, which itself is a fairly complicated function, right? Which is given by this sort of layered structure. You've got all of these weights, biases, some multiplications, additions happening, ReLU being applied, and so on. So this is a fairly complicated structure, right? Now, how do you actually calculate the gradient of this thing, right? So of course, one way would be to maybe you just estimate, use the finite differences method and just estimate. But that would basically mean that for each step in gradient descent, you would have to evaluate this loss function several times, right? Which is not going to be efficient. The other way could be that okay, you figure out what is this gradient as a function, but that is going to be hard analytically and not general, right? It turns out that there is actually a really nice way to calculate the gradient of a function, of any function, mm, given that you know the gradient of each sort of component of this function by this particular algorithm known as the autograd algorithm, right? So this is basically, this algorithm is a general method for calculating gradient of any function of multiple variables. So let's just assume that in our case, we've got just two variables. Of course, the original L has got as many variables as there are members of theta, right? So that is going to be much more complicated, but everything will generalize, as we will quickly see, right? So we've got two variables, right? So now we want a general method for calculating the gradient of any function, right? So firstly, we need to specify what the function is. So in AutoGrad, within this AutoGrad framework, what you do is you just write code to calculate fxy, right? So you'll have written some code in, let's say, Python to do a bunch of different steps and to calculate this function f. And the idea is that once you've done this code, then you can sort of, the AutoGrad framework will automatically calculate the gradients of the of this particular output that you've calculated with respect to the input values for it. Yeah.
No, is there any particular reason why you not gone into full view mode?
Uh, yeah. So the title you're saying?
No, that's okay. I mean, if there's some reason why we can't see the whole slide all together, but that's okay. I mean, if that's
Is this better?
that's fine. Yeah. I just wanted to remind you that it is not in full screen mode.
Okay. Yeah, sure. So I'll just keep it in full screen mode. I just switch to highlighter, and for that I need to do, yeah. Okay. So yeah. So as I was saying, that this is basically some general method where given any function, given the code to calculate any function of multiple variables, this method will automatically give you the gradient of that function with respect to the input variables, right? So how does this work? So let's take some simple example. Like, so let's say that we are going to take one particular function as an example. So can somebody give me a function of 2 or 3 variables that you would like to see gradient of? Any suggestions from the audience? Otherwise, I'll just pick something.
Yeah.
X squared plus y squared whole by 2. Is this the function?
Yeah.
Okay. So let me just make this slightly more complicated. I'll just say, yeah, just in fact, I'll just say 2 times x. Does this also work? Sure. Right. So then when you're writing this function in code, yeah, sorry.
He wants square root of x. By 2 root x.
So is this okay?
Okay, go ahead. Yeah.
Yeah. So firstly, of course, if you're writing to evaluate this function in Python, you would probably have written some. So I don't know if everybody is familiar with Python code. Even if not, just don't think about this is not some. Doesn't have to necessarily. You don't have to look at it as syntactically correct code, right? But in general, you could think that in some programming language you would have written some function like eval_f, which takes in 3. So in this case, it's just 2. So let's say this guy is z. Right? Yes, you would have written this function which takes in three real numbers as input, right? And then it would basically calculate the function as follows, right? You would say that a is some x square, b is some y square, and then c is 2 times z, right? d is x square plus y square, e is, so d is not x square plus y square, then we can basically say d is um, a plus b, and then e is going to be sort of d by e, sorry, c, right? And then you return b. So this would calculate the value of this function for you, right? So another way of looking at this function is as a computation graph, right? You can sort of think of this function as starting with the values x, y, and z, and then constructing various different expressions, and then finally the final expression you get is this return value e, right? So this code, you can sort of think of this code as in terms of a particular graph, right? So this graph will have, it will start with the nodes x, y, and z, and then we construct x square, so y square, right? So this is a and b, and then we have, of course, c, which is 2z, and then we have a plus b, which is let's say d, and then we have e, which is this d by c, right? So d by c. And the idea is that there is an edge between dependencies. So sort of whenever you're taking two expressions and composing them, you get an edge, right? And there's this computational graph that you can sort of follow to do this calculation. It is just rewritten in a slightly different form, right? So firstly, notice something that you can label each edge by a partial derivative, right? So I can take sort of the partial derivatives. So e, for example, is a function of d and c, right? So I can take the partial derivative of e with respect to d and c, right? So I can basically talk about values like this: delta e, delta d, delta e, delta c. Similarly, I can talk about delta t, delta a, delta d, delta b. Then I can talk about delta a, delta x, delta b, delta y, delta c, delta b, right? Okay, so now let's forget about derivatives for a second. Suppose we are given this sort of partial, this sort of a graph, right? What you could do to evaluate this function, if you're given some particular values of x, y, and z, what you could do to evaluate this function is something like follows, right? So let's say given values of x equal to, so give me some values. Let's say 2, 2, 3, or 4, right? Then you could basically follow, go to each node and then follow the expression in that node to calculate the value, right? So for example, then a would get the value 4. Here also b would also get the value 4. C gets 8, then d gets 8, and then e gets 1, right? So we can follow this graph upwards and finally calculate that the value of f, the output that we want, is 1, right? This is nothing but just running the code, right? So another thing that you can parallelly do is also that whenever you're calculating the value of this function, right, you can also calculate the values of these partial derivatives according to the inputs given, right? So we know, for example, that since we're doing square here, the partial derivative is just going to be given with this particular function, right? So partial derivative of this partial derivative delta A delta x is just 2x, right? Similarly, delta B delta y is just 2y. Delta Z delta Z is always just equal to 2, right? Someone tell me what delta D delta A is. One. So someone this is 1, right? What is delta D delta E delta D? Hmm? Yep. And what is this? Delta E delta C is minus d by c. So this is fine, right?
Yeah.
Yeah. So now, what if you think about this particular function? What are we trying to calculate? We are trying to calculate this value, right? We want to know what delta f or in this case e delta x is, right? So if you think about this delta e delta x, so e is really nothing but d by c, right? So we can sort of look at e. If we look at e as a function of x is some complicated thing, but it is really composition of two functions, right? One function is something that takes dn as input and produces e as output, and then for each one of them you're plugging in some simpler function, right? So you can look at delta e delta x as delta d delta x. You take delta d delta x, right? And then sorry, delta e delta d delta d delta x plus delta e delta c delta c delta x. This is just chain rule, right? Correct? So if we know the value here and the value of these partial derivatives, then we can just apply chain rule to get our final partial derivative, right? So we have in some sense reduced the problem of getting this delta e delta x to just getting the partial derivatives of these guys and knowing the partial derivative here, right? So similarly, knowing the partial derivative here by a chain rule can be reduced as, so again, what is delta d delta? Right? So delta d delta x is going to be again some delta d delta a delta x plus delta d delta b delta x, right? So again, knowing what the partial derivative of this guy can be reduced as to this particular problem where you know the partial derivative here and here, and you know the partial derivatives at these particular nodes, right? So in general, via chain rule, you can sort of think of the calculating the partial derivative here as sort of recursive process, right? You To calculate the partial derivative here, you first calculate these partial derivatives and these partial derivatives. Then recursively to calculate the partial derivative here, you calculate these partial derivatives and these partial derivatives, right? And then to recursively to calculate the partial derivative here, you calculate um, these the lower partial derivatives in these guys and so on, right? So there is this particular recursive process, right? But if you notice this recursion, you can sort of also do it in the forward direction. You can, we know that all that we need really are these sort of partial derivatives, right? So if you were to expand out this recursion all the way, we expand out this delta d delta x, right? We'll get some expression. And that expression is again going to be what? It's going to be these partial derivatives along these two edges plus the partial derivative of this guy with respect to x and this guy with respect to x, right? And then you again expand that out, and you'll then now this in general is x squared and y squared, but it could have been any other complicated function. But even then, when you expand it out, it will just be the partial derivative labeled along each of the edge times the partial derivative of the important edge, right? Sorry, is it no? Okay, sure. So if you keep expanding out, right, what you will notice is that the final expression that you will get, it's going to basically be the value in this edge times the sum of the values of these two edges times the sum of the values in these two edges, so on, right? So what you get is that this is basically the key fact behind this autograd algorithm, which is that the partial derivative is the sum of the values along each edge, right? Is this fact okay with everyone?
Yeah, but there's also multiplication along the path, correct?
Yeah. So when is some of the product of the values of along each edge, product of
Yes.
partial derivative values along each edge. Right. So is this okay with everyone?
Yeah, I think so. Yes.
Yeah. Okay. So then see, all that we need to do to calculate this partial derivative is to just keep track of the sum of the products of the values along each edge. Right? So we just need to construct this graph, label each edge by the corresponding values, right? And then just when calculating the partial derivative, we'll just traverse down the graph once, collect all the products, and then take the sum, right? So for example, over here, previously when we were, when we have been given this 2 and 4, we went up the graph calculating the values at each node, right? So now, along with the values, what we will do is we will evaluate these partial derivative functions as well, right? And calculate the values of the partial derivatives. So we get 2 times x, which is going to be 2. Sorry, I mean 4. Similarly, we get 4. And here it's just constant 2, so we get 2, right? This will just be constant 1, so we get 1. This will just be constant 1, so we get 1, right? And then this is 1 by c. So when you c is 8, sorry, so this is the, so this, I think I've labeled it wrong. This guy should be, so delta E, delta C should be labeled along this particular edge, right? Should be labeled along the edge that goes to C, and delta E, delta D should, sorry. Yeah, so delta E, delta D is labeled along this edge, and this is 1 by C. We know C is 8. So this is going to be equal to 1 by 8, right? Similarly, delta E, delta C is D by C squared. We know D is 8, C is again 8. So this is also be 1 by 8, right? And then these are all of my partial derivative values, right? So now if I want partial derivative of E with respect to X, I just look at the path that goes from all of the paths that go from X to E, right? And in this case, there's only one such path, which is this particular one. And we take the product of all of the partial derivatives we're seeing along it. So we take 4, 1 into 8, or 1 by 8, and we get this delta E delta X is equal to half, right? And that makes sense, right? Because 2z is a constant, so this is, yeah. Right? Now, similarly, we can do.
You could plug in the values because you're calculating this, doing the calculation for gradient at each step, I mean, at each point, correct? So you'll, that's why you're plugging in the value, correct?
Yeah. So we want delta E delta X because remember that ultimately we want to calculate this delta L delta theta, right?
Correct. Yeah.
Which would mean that we would want to calculate delta L delta theta 1, delta L delta theta 2, delta L delta theta 3, and so on, right?
That's right. That you're doing it every point.
Yeah, at each and every point. Yeah. And we would want to, so essentially this gradient calculation will happen inside the loop, right? This is going to be repeated until gradient descent is stopped. So for each iteration of the loop, we have to do one calculation of delta L delta theta.
I mean, the basic point is that you can, by doing this graph way of doing it, you can, it's easily incrementally calculatable, right? So where each node in that graph gives the partial derivative for some expression relative to a particular variable.
Yeah. And by incremental, I mean, in the sense that it is incremental with respect to this loss function, right? So as long as you know what each node locally is, right? So locally we know D is just A plus B, right? As long as we know these what these atomic operations are, plus, minus, product with a constant, square, and so on, right? As long as you know what these atomic operations are, and we know, okay, so these are the atomic operations. We also know that what are the partial derivatives of the atomic operations. And since you'll have some finite, like very small number of atomic operations, usually in whatever programming language, you can just define its or write down its partial derivatives, right? So as long as you know that, then doing this graph calculation, all that you need to do is to calculate the gradient is just some evaluation of these partial derivatives, right? So it doesn't really matter how complicated your function is. This will work for any function, no matter sort of how complicated it may or may not be, right?
Correct. Yeah, I think they got that.
Yeah.
Of course, there is a one-time cost of building. I mean,
Yeah, there's some one time.
okay.
Yeah.
So
So
by looking at that expression.
right. So there is a one-time cost of compiling, if you will, this
Yes. Yeah.
right. Yeah.
Yeah, go ahead. Yeah, I think go ahead.
Right. So yeah, so this is basically sort of the idea behind this algorithm, right? Where you construct this graph, and then when you're sort of doing the forward, so then you sort of calculate the gradients in two passes, right? You do a forward pass where you calculate the value at each node, and also when you calculate the value at each node, you calculate the value of these partial derivatives, right? So these light blue and light green values. And then finally, you do a backward pass where you traverse back down via the graph, take each paths, right? Take the products along the paths, and then you will sum them up to get the final sort of gradient, right? So the partial derivative of your function with respect to each input, right? So let's do another example. So if we have something like, let's say, this is something that I think another person, I think this is another proposal that we had, right? So again, this will be x squared plus y squared. Okay, let's call these guys a. Right? But now we also have this b, which is 2x, and then e is e by d, right? So it's basically the similar function from before, but now x has been reused twice. So now notice that this graph actually has got two paths going from x to e, right? the partial derivative of E will then be the sum along these two paths. So just to illustrate that, I've taken this one more example, right? So here again, when we're doing the forward computation, let's take two values of X. Let's say that the values of X will be 2 and 2, right? So we're doing the forward calculation. So then the first thing that we do is, okay, so before that, there is this one-time cost of labeling the edges with the partial derivative. Right? So we have delta D, delta X. And delta A, so delta D, delta X is 2, delta A, delta X is 2X, delta B, delta Y is 2Y.
Hello?
This guy is similarly going to be just 1, 1. This will be minus C by D squared. This will be 1 by D. And this is it, right? Then, yeah, so then again, when we're doing the forward calculation, we know that the X and Y is 2. So the next step, we will see that, okay, what are all the partial derivatives, the values of the partial derivatives, the values along each edge. This edge gets labeled with 2, this edge gets labeled with 4.
There is a question here.
Yeah.
So I wanted to ask about the motivation of why we are doing autograph. So we are basically just calculating the partial derivative, right?
Yeah.
Is it that we are doing it by symbolic computation like simple or something where we are not actually doing this differentials, whereas computer is doing this like elementary differentials?
Sorry, I couldn't hear you. Can come again? So you're
we are actually calculating these derivatives, or is it a computer which is calculating this derivatives, like some symbolic computation or something? If we are actually doing it, then why are we going through so much algorithms?
I guess the point, the question is, why are you going through this rigmarole? Okay, I think that point is not coming out clearly. I think the question is, why are you actually doing it? You're not doing it, by hand. Okay, it's an algorithm that's doing. Even then, it's relevant that this chaining. If I understand, I think the question is why go through this? What is this way of constructing this tree and then doing this bottom up and top down thing by view? Okay. I guess is that the question?
Yeah. If I was supposed to calculate the partial derivative of the calculate of the partial derivatives, I would basically use this algorithm itself myself.
That's right.
Is it that I am not actually doing it on paper, but this calculation is being done by some symbol?
Yeah, it is always being done by some. Correct. Yeah. So the point, if I understand it correctly, is what is this buying? What is this buying us in terms of implementation? This chaining method. You get that? So that's what that point is getting lost.
Yeah, sure. So I'll come to that point. I'll come to what does this look like in terms of, where is what being computed. So firstly here, again, the promise is that you will not have to think about gradients even, right? When you're actually going to use this algorithm as a user, you will only have to think about what this function f is at the function level. So the only code that you will write is this that I've shown over here, right? And then the idea is that the autograd function implementation will automatically sort of give you a gradient. So you can sort of take this output E and then just do sort of E.grad, something like a call like E.grad and say.
This tree, etc., that you denoted is happening inside autograd, is it?
Yeah. It will completely happen inside autograd. So you.
That is fine.
Right.
But if you did not use this method, what method would you be using?
So if you were not able to use this method, you would have to figure out some method of
so once again, the point is not the same question. So by doing this, you're incrementally computing it, and therefore it is more efficient. Is that the point?
So there is 2 points here. So one is there is a point of efficiency, right? And so there's a point of complexity, and we'll look at what how complicated is it to calculate the gradients, right? And so if you look at the complexity, you can see that, conceivably we can't do much better. So one point is that, and the other point is there is also the question of how much work do you need to do each time to from an implementation point of view. If you had written maybe a complicated way of calculating the gradients, but it was specific to this particular neural network, to this particular loss function, right? To this particular number of data points and so on, that may not generalize as well as something like this to say a different network or a different loss function or different activation function and so on, right? So I think if the motivation is not clear, then let me maybe just pause this example for a bit and talk about some of that. So far we have this kind of a gradient descent setup with this kind of a loss function setup, right? Now, if you look at this loss function,
It's not clear.
Sir, I have basically one question. Suppose if I have to differentiate x square, is it that I am putting the 2x, or is the computer differentiating the x square to get the 2x?
sorry, you said if you were to differentiate x square, is it that? And
Is it like, if I, for example, if I was using Python, is it like this x square is being done by SymPy?
it's essentially, so this x square, this 2x differentiation that you have, it's not even like it's being done by SymPy. It's more like for each sort of atomic component that you have, right?
Yeah.
The autograph framework has already given you, it already has some tables which it can refer to get these partial derivative expressions, right? So the idea is that when you write, suppose some function like x squared plus y squared by 2x, right? You're going to write, so in PyTorch, for example, you're going to write it as, you're going to take the PyTorch's implementation of sum. It doesn't appear like that when you write Python code for several reasons, but essentially what you're going to do is you're going to take the PyTorch's implementation of square, you're going to take the PyTorch's implementation of square here, take the PyTorch's implementation of sum, and so on, right? So when you're writing out this sort of a function in Python, and underneath that code in the background, this table is getting, so this graph is getting constructed, and then AutoGrad will have a table of references for each component. So each one of these nodes can be one of a few component or atomic functions. It can be squared, it can be multiplication, it can be addition, it can be division. It can also be things like, the table is fairly large. It can also contain things like log, sine, and so on. And with respect to the table, there are symbolic entries for each one of the partial derivatives of this function. So for example, with something like sine, there is only one possible partial derivative, which is the derivative with respect to its input, and then there is a symbolic entry for that. So with respect to sine, the table will contain the corresponding expression for derivative of sine, which is going to be cos, right?
Yeah, so this is, in other words, a modular approach, right? So that there is some in the table, there is some predefined way of computing these derivatives for different functions, and then your f can be a complicated expression that
Involving those functions.
Yeah, involving.
And it can be any expression involving those functions.
I think so. Okay.
Yeah. And so then the idea is that then this AutoGrad method then will work for any complicated expression involving those functions, no matter how complicated it is, right?
Yeah, I think the point is clear.
Yeah. So that is so was that does that answer your question?
Yes.
Okay. Yeah. So just let me work through this example, and then I'll maybe make this point even more explicit. But so in this case, what we're doing is, so we have this 2x over here, right? So delta x gets value 4. Similarly, this also gets value 4, right? The values along these edges for the partial derivatives are just 1, right? We calculate the value of x, so value of A is again 4, B is again 4, D is going to be something like in this case 2x, which is also 4, right? And then the value around this is going to be So yeah, so then we'll calculate value C, which is A plus B, which is 8. And then the value around this is going to be C by D squared, right? So that is 8 by 16. So we get half, right? And 1 by D. So D is 4, so that we get 1 by 4. And then finally, the value of the output value of the function E by C is C by D, sorry, it is 8 by 4, which is 2, right? So now if we look at the partial derivative, let's say that we are looking to calculate delta E by delta X. So again, we look at all the paths, right? So in this case, there are two paths. So the first path will give us half times 2, plus we have a second path, which is going to give us, so the second path is this path, which is going to give us 1/4 times 1 times 4. So delta E by delta X for the particular input value of X that we've chosen comes out to be 2, right? This is what the algorithm becomes, right? So let me sort of now, because there was a few questions, so let me sort of make clear what this algorithm will look like from the point of view of the implementer, and what is happening underneath within the actual implementation, right? So again, let me go back to this particular example. So let's say that we have some Python code that looks like this. Right. So what is going to happen is during okay, so again let's just x and y and 2 times x just for consistency. So what's going to happen is that from an implementer's point of view, whenever you want to sort of get the partial derivative, all that you would have to do is write some code like this, saying that let's say some variable v is equal to, you pass in some 2 comma 2, right? And then you say v dot grad x, or let's say v dot grad with respect to the first variable. This, if you print, it should give you the value of function delta f delta x at x equal to 2, right? This is what the code that is going to call AutoGrad look like. So when you're using AutoGrad, all you have to do is define f, or evaluate f, right? So you have to only write the forward computation, only the forward direction of the code, and then you get the gradients automatically. So you just do some call, or you just read off the gradients, right? Right. So this is because this value v contains the gradient information. So because if you notice, the value v is coming because we're evaluating the function f at 2, right? So then when we do v dot grad, the gradient that we get is with respect to basically we get the gradient with respect to the value that we computed f at, right? So I'll make this clear in a little bit when you see what happens in the sort of backend, right? So in the backend, what happens is two things. So one thing is that in compile time, this gets converted into this sort of a graph, right? Right. So what you get basically is some graph like this. And this gets the graph by looking up the looking up all of the gradient tables for atomic expression, right? Right? Then when you're actually doing the calculation, two things happen. So you're calling f of 2 comma 2, right? So you're calling f with x equal to 2 and 2, right? So when this step is happening, on the other side, on the sort of back end, what happens is that this graph gets you end up doing the forward computation with respect to this graph, right?
So I'm a little confused about what you mean by V grad of 0. What is that 0? In square bracket that you have?
So yeah. So this v dot grad will be sort of a array, if you will, containing the partial derivative with respect to x and y. Right?
So 0 is with respect to x and 1.
Yeah.
Okay, I missed that. Okay, I missed that. So when you say v grad of 0, you mean you want to compute the derivative at 2 with respect to x. That's what you mean.
Yeah.
Okay.
So then the idea is that once you've defined this f in this way, and this graph is in
I
place.
think we're getting a little too much into the implementation here. I mean, I think, do you need all this detail to?
No, you don't read. I mean, as a user, all you need to know is that you can just call it and then get rid of the gradient automatically. But I mean, just to make things clear what's happening in the backend, what is going to happen now is that whenever you're going to call the function, all of this forward computation is going to happen, right? And then the backward computation is going to happen, and it's going to store not only the value, so the time, so whatever return you get out of this function, it's going to contain two things. It's not only going to contain the original value that you get at the output of the function, but it's also going to contain the gradients of the function with respect to the inputs 2, 2, right? So yeah, so in this step, what is going to happen is the forward pass, and then store the value of function at v dot value, let's say, and then you're going to get the backward pass, and then we are going to collect the gradient of with respect to x and y for given values of x and y. And then we're going to store that in v dot grad, right? This is essentially what is happening in the backend. So then finally, when you want a gradient, you just read off the gradient, right? Okay. So this is basically what the autograd algorithm is. And then, as I said, the main sort of benefits is two things, right? So we have the benefits of this is twofold. One is generality. It does not really depend on the complexity of the function. So for example, if you're using this, all you have to do really to calculate the gradient of a neural network is to write some function to calculate the values of a neural network. Once you know what the values of how to calculate the values of a neural network given a bunch of inputs, the autograd algorithm is going to automatically take care of the gradient part for you, right? So we only need to write forward direction. So we only need to implement forward direction. And what that means is that anytime we want to change anything in the implementation again, we also only have to do it in the forward direction.
So just to be clear, what was the forward direction?
Yeah, the forward direction is, I mean by forward direction, he means, correct me if I'm wrong, so just evaluating the function, correct?
Yeah,
That's
yeah,
what you mean by forward direction.
yeah, yeah, yeah.
Yeah, I mean, as a user, I understand that you need to save it, but still in the background, it has to do all the work, okay, of traversing the street and doing backup, correct? I mean, there's no magic in here.
No, so that work, yeah, so I'll come to that amount of work. There is no magic here, right? But from a user perspective, with respect to this first benefit at least, it is that you only need to implement the forward direction. So I'll say what I mean by that. So for example, if I were to, if I, had some nice way of calculating this function, an alternative would be something like this, right? As a user, I implement this function, right? And then I also separately implement delta f delta x of x and y as, I calculate out whatever the expression comes out to be, right? So I think in this case, the expression would come out to be something like half, sorry, half plus you get y by x squared, so y squared by 2x, so that will be minus y squared by 2x squared, right? So we get this will sort of be the implementation, right? So you would have to write this as a Python function, and similarly you would have to do it for delta f delta y, right? And so on. But then suppose I want to change something and I change this guy to y. So now all of these things will need a lot of changes, right? Whereas with this autograd method, what you would have to only do is you only need to change, with autograd, you only need to change this implementation. And all of this, the changes that would have propagated to here gets handled by the backend. There is no magic happening. It is still, the work is still being done, but you don't have to do it. It's being done automatically by the backend. And it is happening in compile time. So it's only a one-time cost, right? So most implementation is a just-in-time sort of compiler that handles this. And that is going to be a one-time cost, right? So for the first time you run the function, you probably have to incur the cost of creating this graph. But then after that, it is going to be you don't have to worry about the cost as well, right? So firstly, you don't have to make messy and error-prone implementations of the gradient yourself, which means that this function f can be as complicated. You don't have to worry about it from an implementation point of view. And from an actual computational cost point of view, that is where my second point or benefit of gradient descent comes in, which is that the cost, so constructing graph is a one-time cost that can basically be ignored. And then evaluating gradients, that is going to be just linear in the size of the graph, right? So that is going to again just be so the order is going to be about as costly as the forward direction, right? Correct. So you are incurring some one-time cost of constructing this graph, which is also not very large, but that is there. But then every time you want to calculate a gradient, the cost that you see is only as much as the cost of the actual forward direction computation, right? So previously, what were we doing? So suppose that we were only calculating the value, we don't care about the gradients, then all we would do is we would go up the graph and label each sort of node by the value, right? If you think about a code executing this just linearly, it would basically also be doing the same. There would not necessarily be any graph data structured, but you can still sort of think of the code as doing exactly the same steps, right? Exactly the same complexity and number of steps. Here we're doing the similar thing in the forward path, but additionally we're also labeling the edges. And anyway, the number of edges is going to be similar to the number of nodes. And then you have this backward pass, and in this backward pass, we're calculating these the product along these paths.
We're running out of time. Okay.
Oh yeah,
So it's all just for computing one gradient step, correct? Which you're describing.
yeah, yeah. But yeah, but do you see that the complexity added by this gradient operation is going to just be of the same order of magnitude as the forward path computation, right? So this is sort of the one that you don't general. So you don't have to you don't only want to implement the forward direction. You don't have to worry about implementing the
For
direction.
example, one person here had a question. Suppose you introduce a new function, a new, suppose like he said instead of 2x, you have 2 square root of x. Okay? Of course, you are introducing a new building block function, correct? So of course, you have to write at the compilation phase how exactly you do these partial derivatives for each of those new operations that go into the final unit, correct? So that there's no magic there. You will have to write it up.
No, but yeah. So I'm saying, of course, that if you introduce a new building block, then you have to write it. But
Yeah, that's what. So there is, okay, for the same set of building blocks, if you're using the same set of building blocks in defining different functions, I can understand this gives a very nice modular way. Okay, but it is for a fixed set of building blocks, correct? If you change the building blocks itself, then of course you'll have to, write a new compilation, correct?
yeah, if you change the set of building blocks, then you will. But the idea is that with the building blocks is
No, I think that answers that. Okay, so there is some additional work if you enhance your building blocks. That's my limited point. Okay.
yes, of course. Yeah.
Okay, go ahead. Yeah.
Yeah. So yeah, if you change the number of building blocks, there will definitely be some additional point, like additional work involved. But then, yeah, so you would have as many building blocks as atomic operations in your language. So if you're writing in Python, for example, you would have one building block for each sort of possible operation that you can do within Python, or atomic operation that you can do in Python. Right? So the idea is that whatever code you may want to write to define any f in the forward direction, it will only involve whatever atomic operations you can do in Python, and there will be one building block with respect to that. Of course, if you want to go beyond that, then you would have to do some extra work. But whatever you can do within whatever underlying language you're working in, usually an AutoCAD implementation will support all of those possible atomic operations.
Yeah. Okay, please move on. Yeah.
Yeah. So this is all I had with respect to AutoCAD. Does this make sense?
So which part is backward propagation? So this is all so far you have described for computing the gradient at a single point, correct? You have to repeat this, isn't it?
Yeah.
The
backward propagation is basically this step when we are going back down the graph.
Okay, that's what you call. Okay.
Yeah. To calculate the gradients, we're collecting the the product along each path, right? So then we're sort of going back down along this to calculate the product along each path or collect the product.
AutoCAD does for you automatically, is what you say.
Yeah.
Okay. There's one more question.
suppose I have function x plus x, the
Mhm.
other function there is only 2x. So while constructing the graph, I mean, how the x plus x and the 2x will look like. 2x will be just 1x, that is 2 is multiplied with x. But the 2 plus x plus x, how will it construct?
Right. So it'll look like two different graphs, right? So x plus x. So when I say a graph here, it can have multiple edges between same nodes, right? So x plus x the graph will look something like this, where you have two edges to one node which is doing some plus operation, right? And this node really is doing plus of x, or plus of two things, two nodes. Both of those nodes turn out to be the x, right? So this is what the graph will look like. Whereas in 2x case, the graph would be x, and then you send it to. Depends on exactly how you have set up your your building blocks, but usually what they have is some multiply by constant building blocks, right? So you have some, yeah, multiply two, where two can be replaced by anything. You'll have a set of building blocks of 2, 3, 2.5, whatever. Does this answer your question?
Yes. So it cannot differentiate between these two blocks. They are both the same. It cannot.
Yeah, both are the same, and yeah, it's not like the automated algorithm at any point realizes that they're the same, right? Like, so both of them are same as functions, but they're different as expressions, so they lead to different graphs. But ultimately, when you do the computation, everything will come out to be the same, right? But yeah, underlying they have two different graph structures. Yeah.
Any other questions on this part of the thing? Okay. Yeah. I'd like, I don't know what is the rest of the thing that you have, you plan to cover. Okay, there's more things. Yeah. I thought you had this picture where you had this a loop, no? Can you go back to that?
Yeah.
Yes, okay. This is all what you described was just this one step of computing delta L by delta theta, correct?
Yes.
Okay, now, and I'm hoping you will cover that. So, but you have to keep doing this repeatedly until, yeah, you explained last time.
Yeah.
But the question is, there is something, in the training process, there is some epoch and those kinds of things. I mean, you're getting into that.
That is there in this one, and then
Okay, that's what you get. Okay, that's what
yeah. Okay, so now let me talk about one more sort of optimization that one does to the training, which is called.
In terms of time, I think since it is, we want to finish this. Is it okay if we go till 5 o'clock? Yeah? Okay. So we have till 5. Yeah. 20 minutes.
Okay, sure. Thank you. So yeah, so there's one optimization that one does, which is called stochastic gradient descent, right? So notice that if you go back to the loss function, the loss function was average over I of some things. This is some whatever cross entropy equation. But whatever we're doing this is averaged over I. Where this I is basically the index of the input output examples that we have, right? So this average can be expanded out as 1 by some capital N, where I goes over 1 to N and sum over this, right? So now this can get very large, right? So you can have a huge number of input output examples. So for example, in the MNIST data set itself, there are some 60,000, and that is a very, very small data set. If you talk about the modern state of the art, right? ChatGPT has been trained on quote unquote the all of internet, which is some petabytes of data. So remember that so far what we see.
That you have number of nodes, you mean?
This capital N?
No. Yeah, capital N.
Yeah, so capital N is the number of
the size of the sample.
yeah. That's the data set. The size of the number of input and output examples that we have.
I mean, I got confused with the number of nodes now.
No, yeah. So it is the number of input and output examples that we have, right? So now, number of input and output examples is some 6,000, right? And I mean, general, with ChatGPT, more like, so of the order of 10 to the power, easily to the power 9, or even sometimes 10 to the power 2. So yeah, I mean, it's really some other things need to be done. But if it is something of this order of magnitude, right, then each step of gradient descent is going to be very slow, right? And why is that the case? Because even with the appropriate algorithm, and what you need del L del theta is really linear in the amount of calculation it's basically proportional to the amount of calculation you need to calculate this L in the first place, right? Now, if your L is a loop that takes these many data points and runs over all of them, each step of gradient descent is going to be very, very slow, right? L itself is going to run 10 to the power 9 times. Then, if you run autograd algorithm, each time when you're calculating the gradient, you have to do at least these steps, right? So each step is going to be very slow.
So Nidanta, you're breaking up a little bit, so you need to speak into the microphone.
Yeah.
Yeah, we'll try.
Yeah. Okay. So what I'm saying is, see, the time taken by each step of gradient descent is proportional to, so each step takes as much time, is about as much time as computing L does, right? Which is basically a sum of blah blah blah, right? And this sum is going to be over 10 to the power 9 things, right? Which is going to be very slow, or which is going to be quite slow because we are having to calculate a huge sum, right? So we can't really iterate over the entire data set at each step of the training, right? Because that would basically mean that given the same budget in terms of time, you end up doing much fewer steps, and that means that you can fail to reach the optimum, right? You have to train for days and weeks and years, and even then you might not ever reach the optimum, right? So then what do we do? So notice that this is an average. So instead of exactly calculating the average, we can just estimate the average, right? If we randomly choose some subset of the 10 to the power 9 points and then do the sum, we will get an estimate of it. And this subset size can be smaller than 10 to the power 9. It can be something like 1,000, right? Which is much more tractable.
So you estimate the average of L theta.
The average over all the data sets that is inside L theta. So L theta itself is an average, right?
Okay.
And we're estimating this average by taking a smaller set of samples, a smaller subset of the whole samples that we have, right? So that is the key idea behind stochastic gradient descent, that we just estimate the average, right? So how do we do that? They do that by sort of splitting the data into mini batches. And each mini batch, for our purposes, let's say that it's something like 1,000 samples, right? So then what we do is, instead of calculating the original L theta, we calculate a smaller estimate of L theta, let's call it LE theta, which is going to be sum, and this sum is being over the data set, it is going to be over one mini batch, right? Of C and so on, right? And then with respect to this sum, we'll update the gradient, right? So we'll set theta to be theta plus delta L theta by delta theta, right?
Okay.
So 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 this delta LE is with respect to, let's say, mini batch number I, but I'm saying, this is cross entropy of the input J and so on belongs to batch PI. So on, right? So what we have done is we had an entire huge data set of 10 to the power 9 things, and we split it into some mini batches, each of around 1,000, so 10 to the power 3 things. And then what we do is we take the average over these and minimize that. Take the average over these, minimize that. Take the average over these, minimize that, and so on, right? So we do this until we get to the end of the data set, and then we shuffle the data set, split it into mini batches, repeat again, right? So once we get to the end of the data set and shuffle things, that is usually called one epoch. One epoch is going over the entire data set once. So if you have, in this case, 10 to the power 9 data points, and each mini batch is 1,000, then one epoch will sort of be 10 to the power 6 training steps, where you're 1,000 each time, minimizing the loss on those 1,000, taking a difference of 1,000, those 1,000, and so on, right? And usually we train for multiple such epochs, right? Now,
Yeah, one question I have.
Yeah.
How do you you hear me?
Yeah, I can hear you.
Okay. But how do you? I know you mentioned the size of the an epoch, okay, the mini batch. How do you decide what sample? How do you distribute the various samples across these epochs, mini batches?
Yeah. So the way we distribute the various samples among mini batches is we will shuffle the entire data set and then split it into mini batches, right? So
That's what the shuffling takes care of.
Yeah.
Okay, so you shuffle at random, is it?
Right, at random, and that will sure that will basically make sure that each mini batch sort of sees a random subset of the total number of samples that we have.
Okay.
Right. And so one point that I would like to make is, how do you sort of choose what is the size of the batch, right? So the values inside the mini batch, the exact samples inside the mini batch is going to be random, but this is a parameter that we actually have to decide, right? So in general, it will be trial and error.
When you say too big an epoch size, do you mean that? What is too big?
Too big of a mini batch size.
Mini batch size. Okay.
Yeah. So how many samples do we train on at each point, right? So if it is too big, that means if a mini batch is too big, then we'll get bad performance, because then we're basically back to the same situation we were iterating over 10 to the power 9 things for each training step, right? If it is too small, then the estimate of loss that we get is too noisy, right? So if it is too small, let's say there is only one sample, right? So then essentially what we're doing is we're looking at only one input output example and modifying a neural network so that it works better for that example, right? So then what can happen is you keep doing a bunch of these very noisy modifications, and you keep coming back to the same point that you start with, right? So you can have maybe one example that is, let's say, a numeral 1, right? You make your neural network better at detecting 1, but then you're making it potentially worse at detecting everything else. And then you see a 2, and it becomes better at detecting 2, but it becomes potentially worse at detecting everything else. In particular, the changes that you made when it got better at detecting 1 in the previous step can get lost, right? At least would want to detect 1 and 2 together, right? but then you might lose out on, say, if you do two at a time, you might lose out on, if you are getting better on one and two, you might lose out on three, right? So you'd want to see some amount of variety that is there in your data set at each training step, because otherwise you'd just be steps that negate each other. In statistical terms, what that would mean is that the estimate that you're getting is sort of too noisy, because the estimate is based on too few samples, right? So yeah, so you don't want it to be too small, you don't want it to be too big. Where exactly in the middle, that is usually there is a lot of literature out there, but fundamentally speaking, nothing better than trial and error is expected to be obtained there. So any questions about this? Stochastic gradient descent? Okay.
Yeah, go ahead. Please.
Yeah. So the sorry, it's a question?
No.
Okay, sure.
Go ahead.
So finally, let's talk very quickly about overfitting. So let me just focus on this particular image. So let's just go back to this, simple of a parameter is function of a parameter that we had seen before, which is a polynomial, right? So let's say that you have some situation like this, some bunch of data points, right? So blue circles and red pulses, they are all your data set, right? So let's say that while training, you're seeing the blue circles, and then when you finally take your model and deploy it in the real world, you get to see are these red pluses, right? So it's kind of important that, intuitively speaking, they are from the same distribution. So what we're really trying to learn in this machine learning context, a function for this distribution, right? And let's say that we are using a polynomial for that. It still works for the neural network case, but with the polynomial, it's kind of easy to see the example, right? So as you keep making polynomial more and more complicated, it will learn to fit these blue points better and better, right?
So what is the polynomial here you're talking about?
So the polynomial is just basically, so this is a two-dimensional, it's a function of one variable with one output, right? So it is
making the loss function or what? No. What is the polynomial you're talking about?
So the polynomial is basically the function underlying this graph. So there is this blue line, right? So the polynomial here that I'm talking about is going to be some function that is training. So polynomial is a parameters function approximator, right? And the parameters are going to be the coefficients of each. So it's going to be some a times x, a0 plus a1 times x plus a2 times x squared, right? So this a0, a1, a2 can be my coefficients.
Yeah, this is what the polynomial goes into the loss function.
Yeah, it goes into the loss function, right? And then let's say the loss function is just going to minimize the average error, right? So the average error is going to be the average error from these points and so on, right? So then as we get more and more complicated, that is higher and higher degree polynomials, we'll be able to average the error better and better, right? But at some point, we might get to a situation like this graph, right? Where you see, notice the polynomial actually passes through all of the points precisely. So the average error here, if you look at the loss is actually 0, right? Because the polynomial passes through all of the points precisely. But then if you take this model and try it on the real world, now you're going to see these red points, and you're going to see huge errors, right? So for example, if you take a red point that would come from here, you see this huge error over here, right? So although you have now a polynomial that actually gives you zero loss, that means, according to the training process, this polynomial is perfect. When you deploy it in the real world, you would find out that no, this polynomial is actually performing really badly, right?
It still makes sense, yeah. You know what the red dots are, huh? The test data, right?
Yes. So we're not doing well on the test data. We're calculating the loss with respect to some training samples, and we're doing extremely well there. But we're not actually going to do well on some test data that we'll now see in the real world, right? So Yeah, so this is basically, this phenomenon is basically called overfitting, right? Where the intuitive idea is that
Have 5 minutes here.
yeah, sorry.
You have 5 minutes, I said. Yeah.
Okay, yeah, that's all I need.
You can always, use the beginning of the next class to tie up loose ends. But 5 minutes is the cutoff. Yeah.
No, 5 minutes. I'll. That's all I have here. So this is basically the intuition behind overfitting, where the idea is that you end up fitting your training data very well, but the, the training data is not really necessarily a faithful representation of the real world distribution, right? It is basically the real world distribution plus some noise, right? I mean, in the image recognition case as well, for example, there might have been some noise in the scanner. So if somebody has written this image, this digits out in on a copy or something, they have converted into a digital image by some scanner. That scanner can produce some noise, right? So if you were to train your network too well, the network might actually learn to classify the digits based on some distribution on the noise that came from the scanner. Maybe on the day that you were classifying all of the ones, there was some phone near the scanner that created some noise, and somehow that minuscule amount of noise, the network, because you've trained it really well, it learned to pick up on that and it's making its decision based on that, right? From a statistical point of view, you can also imagine that there will be some noise, and you can, of course, if you get a complicated enough function, you can make some arbitrary way of drawing a line to distinguish between the kind of noise you've seen for class 1 and the kind of noise you've seen for class 2, right? So for example, in this case, if you get a very high degree 9 polynomial, we can of course make it pass through all of our points, but even if you're 1,000 points, if you take a degree 1,000 polynomial, you can make it precisely pass through all of the points, right? So then, but most likely it will be some zigzag line that passes through all of the points. This is the real distribution, the real picture completely, right? So it's going to have very low training loss, but it's very high test loss. So this is this problem of overfitting. And as you train, the way you would detect this, you'd see that the training loss goes down and the test loss goes down. But as soon as overfitting would start to kick in, what one can expect is that the training loss continues to go down, but the testing loss will actually continue to go up, right? So the testing loss is basically a loss that you would get if you were to try the function out on a completely different data set that you're not training on, and that loss begins to go up, right? So this is something that one has to be careful of when they're training a neural network, which is that you only sort of you train it on some data set. You also evaluate it on a separate data set.
Yeah, let me see.
And whenever you see that this new data set that you're evaluating on, whenever you see that the loss there is growing, you just have to stop the training process. Yeah.
Hello?
Yeah. Hello? Hello? Hello?
I know this is abrupt ending, so we will smoothen it out next time.
Yeah, but this is basically all I had. Are there any questions?
In there, so classes are.
Hello?